Okay, we have here today on the board an integral that we want to generalize. We have the integral from a to b of cosine to the nx dx. And I got this idea from a suggestion in the comments. I recently did a video where I did cosine to the 2023x. I believe it was from pi over 2, from 0 to pi over 2. I can't remember exactly. But there were some questions in the comments about maybe doing this in a more general form. Just to clarify on the n value, I think we want the n to be an integer greater than 0. To start with this, what I'm going to do is we're just going to use the power reduction formula for the indefinite integral for cosine. So now we have here our power reduction formula for cosine. Now there's a really similar formula as well for sine that works basically the same way. At the end of this video, we'll kind of touch on that and how we would do this if this was sine. And if you're not familiar with this formula, I did videos on both the power reduction for cosine and sine, so I can provide a link in the description of that. Now a couple important takeaways here. We just notice here that we don't actually solve our integral with this formula, we just reduce it. So here we get back cosine just reduced by degree of 2. We have n minus 2 here. So this value here is actually I to the n minus 2. So when this is a large exponent, if you had to do this out for an indefinite integral, it would be super tedious because you're just reducing by 2, reducing by 2. So if you have 2023, you have like 1,000 integrals. Now the next thing we want to notice here, we just have these generic bounds b and a. That's kind of a problem here because if b and a can be anything, well, then we're going to have this term here, and we're in the same situation. Again, like if n is something like 2023 or 1,000 or a million or whatever, then we've got a million terms. We don't want that. So what I want to do is actually kind of put some restrictions on this b and a. If I say b is like j, where j is some integer times pi over 2, and then for our a value, we'll do the same kind of thing. We'll say a is k, some integer k times pi over 2. You'll notice that what happens is whenever our j or our k is even, you'll end up with like pi, 2 pi, 3 pi. Well, for all those terms, our sine value is going to be 0. And then if you have some odd number, like let's say j is 3 or k is 1, at pi over 2 or 3 pi over 2, all these cosine terms are going to 0. By doing this and making j and k an integer, either cosine is going to be 0 or sine is going to be 0. They're multiplied together, and this term goes away completely because it's always going to be 0. So this step is really important. You'll notice in like any contest problem you see, I don't think I've ever seen it where it's not either like pi over 2, pi, 2 pi. We need to have this in order for this to simplify nicely. So looking at this formula with this term here basically wiped out, we still have this problem where we're only reducing by 2. So for our I sub n value, we end up with this. Well then what's our I n minus 2? Well, we can actually find that value just using the same formula. If I plug n minus 2 in for n here, this becomes n minus 3 over n minus 2. And then for the integral part, this just becomes I n minus 4. And of course, we could do this over and over again a million times until we see a pattern. So after we've done this a million times, we go back to the thing that we want. We want this I sub n, that's our goal. And we can kind of just recursively plug in values. So doing that, what's going to happen? We have our n minus 1 over n. Now I n minus 2, we take this value and plug it in here. We have our n minus 3, n minus 2. Then we have this I n minus 4, but then we plug this one in. So hopefully you can see where it's going. This is just going to go on and on like this. Well, what's actually happening here with each term decreasing by 2, that's actually the definition of the double factorial. So I can actually express this whole long thing just like n minus 1 double factorial, and the same thing here in the denominator. I can write this just as n double factorial. And just to be clear, if you're not familiar with double factorial, like if we have 5 double factorial, that's the same thing as 5 times 3 times 1. And so 6 double factorial would just be 6 times 4 times 2. And just notice for the even number, we end on 2, and on the odd number, we end at 1. So we'll just say for this case, our n is even. And then really the same thing, we can look at when n is odd. This is going to be the same basic formula with the double factorial, but then the last term we need to find is I1. Imagine if n is 3 here, well then here you're looking for n minus 2 or just I of 1. So this is why for the odd case we end at 1. Now at this point, this is pretty good for a formula, but we can do a little better because we can actually just calculate these values. So for I of 0, this is going to be really easy. We have our a to the b, and we just have cosine of n0. So we have cosine of the 0. But cosine of 0 is just 1. We're integrating 1. So we get x from a to b. And so this is just going to be b minus a. And now there's also different formulas to express the double factorial as a single factorial, so you could reduce that with another formula, but I'm just going to leave this in terms of double factorials. But now we can just do the same thing for I of 1. So again, here's our integral, and now we're just integrating cosine of the 1, but that's just cosine, so when we integrate that, we're just going to get sine of x evaluated from a to b, and so this is just going to be sine b minus sine a. So I'll just take that and we'll plug that in here for I of 1. And just one other thing I want to notice on this, because again, the way we defined a and b to be multiples of pi over 2, this piece is going to simplify really nice. Like that's why a lot of times this can be 0. If b is just pi over 2 and a is 0, then we just get a 1 here. So this part is usually really easy to calculate. Okay, now before I finish up, just one more thing I want to discuss. Now, what if this wasn't cosine? What if this was sine? Well, it's really similar. I'm not going to write out the formula for the power reduction, but it's almost the same thing. I think there's a minus sign in front, but there's still a cosine and sine. So it has this same basic form with cosine and sine. If we plug multiples of pi over 2 in here and we have this same piece, it's going to go to 0 and it's going to be the same type of thing. So in our formula, this term's going to go away. We're still going to have the n minus 1 over n. This here is going to become sine of n minus 2. So it's still going to be our I n minus 2. So what happens is everything is basically working the same way. We're still going to have this n minus 1 double factorial. We're still going to have this piece here. So what we can do is put together our formula for sine really quick. So here's our basic formulas for sine for the even and odd case. Same thing we had before. So again, we need to find our I of 0 and our I of 1. Well, I of 0 is exactly the same because we end up with, we're doing an integral of a to b, and now we have sine to the 0. But again, sine of the 0 is 1, and so we integrate this. So it's just the same exact thing, and for this, we're going to still have b minus a. And now for I of 1, it's just a little bit different. Now remember, when we did this before on cosine, we were integrating cosine of the 1. So now we're integrating sine to the 1 of x. So the only difference is when we integrated cosine, we got sine. When we integrate sine, we get minus cosine. So here we have minus cosine from b to a. So what's going to happen is that sine is going to reverse our expression. So here we had sine b minus sine a. What's going to happen here, because of that minus, we're going to end up with cosine of a minus cosine of b. Okay, and so that's it. So for cosine and sine, you can't really reduce it to one formula. You can reduce it to an odd and even case for each for cosine and sine. But I find this pretty useful whenever you have like a large exponent on your cosine or sine. So we'll stop it there. Thanks everyone for watching. Have a great day.